A spider is going about its life, spinning webs, catching prey, doing spider things, when suddenly something grabs it, injects it with venom, and rewires its entire brain. From that moment on, the spider doesn't belong to itself anymore. It belongs to a wasp. And here's the part that'll keep you up at night: the spider doesn't even try to escape. It just obeys. Stay with me, because this story only gets darker. We're going to cover how this wasp pulls off the mind control, why the spider's web transforms into something almost architectural before the spider dies, and the reason scientists think the venom works the way it does, which tells us something genuinely unsettling about how all of our brains might be manipulated. Let's start at the beginning. Deep in the forests of Central and South America, there lives a small parasitic wasp called Hymenoepimecis argyraphaga. It's not much to look at, maybe a centimeter long, unremarkable coloring. But what it does to the spider Plesiometer argyra is one of the most sophisticated acts of biological manipulation ever recorded on this planet. The female wasp finds a spider that's actively sitting in its web. She lands on it, briefly paralyzes it with a sting, and then, while the spider is immobilized, she glues a single egg to its abdomen. Then she flies away. The spider wakes up. It goes back to its life completely unaware that it's now carrying a passenger. For weeks, the wasp larva feeds on the spider's body fluids through a tiny hole in its abdomen. This is gruesome enough on its own, but the spider stays alive the whole time. It hunts. It eats. It maintains its web. From the outside, it looks completely normal. And that's intentional. A dead spider is useless to the larva. A living, hunting spider keeps it fed. But here's where the story shifts into something else entirely. About a week before the larva is ready to pupate, to transform into an adult wasp, it injects chemicals into the spider's body. And this is where the zombie part becomes literal. The spider abandons its normal orb-shaped web. It tears the whole thing down and rebuilds it into something radically different. Instead of the classic concentric rings you'd see in any garden, it builds a reinforced structure, dense, tough threads all converging on a single central platform. Researchers who've studied this call it a resting web. It looks almost like a hammock engineered for something specific, because it is. It's a cradle for the wasp's cocoon. The spider builds this structure it has never built before, that it would never build under any other circumstances, and then it just stops. It sits in the center of what it created. It doesn't eat. It doesn't flee. It waits. And then the larva kills it. Once the spider is dead, the larva sheds its skin, drops the spider's body, and spins its own cocoon, hanging it right where the spider built that reinforced platform. The structure is strong enough to protect the cocoon from rain. It holds the cocoon off the ground. It was, from the very first thread, built to specification by an animal that had no idea what it was building or why. Now here's the scientific question that makes this even stranger, and it's one researchers are still actively debating. How exactly does the venom change the spider's behavior so precisely? Here's what we know. Studies published in the journal Behavioral Ecology and examined by researchers including William Eberhard at the Smithsonian Tropical Research Institute found that spiders under larval influence produce webs with structural features that overlap with normal pre-molting behavior. Spiders, right before they molt their exoskeleton, naturally build stronger, simpler webs and go into a kind of resting state. The wasp's chemicals may be hijacking that exact same neurological pathway, essentially tricking the spider into thinking it's about to molt, but pushing that instinct into overdrive. Think about that for a second. The wasp isn't writing new code into the spider's brain. It's finding an existing program and exploiting it. It's like someone taking your instinct to flinch away from danger and chemically rewriting it so you walk toward danger instead. Quick tangent here, because you genuinely need to know this. Hymenoepimecis argyraphaga is not the only wasp pulling off something like this. The jewel wasp Ampulex compressa does something equally nightmarish to cockroaches. It stings a cockroach directly in its escape reflex center, then leads it by the antenna like a dog on a leash back to its burrow. The cockroach doesn't run. It just follows. The wasp lays an egg on it, seals the burrow, and leaves. Scientists have actually traced the exact neurotransmitter, octopamine, that the jewel wasp depletes to make this happen. The cockroach's will to flee isn't destroyed. It's chemically blocked. The The cockroach can still walk. It just won't. There is something philosophically disturbing about an animal that is physically capable of saving itself but has been chemically convinced not to try. Back to our spider wasp, and here's the part of this story that I think is the most extraordinary. Researchers tested what happens if you remove the larva from the spider right before it would normally start inducing the behavioral change. The spider snaps out of it. It goes back to building normal webs within a day or two. The manipulation is reversible. The spider's brain isn't damaged, it's being actively overridden in real time by whatever chemistry the larva is pumping into it. Remove the source, and the spider comes back. That means the larva is continuously dosing the spider. It's not a one-time injection. It's an ongoing chemical conversation, except the spider doesn't get a vote. And here's the open question scientists still haven't fully cracked: the exact cocktail of chemicals involved hasn't been completely isolated. We know polyamines are likely involved. We know the spider's molting hormones are probably being exploited. But the full molecular recipe for how you turn a spider into a precision architect that builds you a home and then dies in it, we don't have that yet. It's one of the genuinely unsolved puzzles in behavioral ecology, and researchers around the world are still working on it. What makes this wasp's manipulation so staggering compared to others in the animal kingdom isn't just that it controls the spider, it's that it controls the spider toward a purpose more useful than the wasp could achieve alone. The spider builds a structure better suited to protecting the cocoon than anything the wasp larva could spin itself. The wasp evolved to outsource the hardest part of its own survival to the very animal it's parasitizing. This is nature operating at a level of complexity that honestly feels like it shouldn't exist. A larva the size of a sesame seed has, through millions of years of evolution, developed a pharmaceutical toolkit precise enough to redirect an arachnid's entire behavioral repertoire not randomly, but toward a specific, functional outcome. So here's the question I want to leave you with. If a wasp can evolve a chemical key that unlocks and reprograms another animal's deepest instincts using pathways that already existed in that animal's nervous system, what does that tell us about the vulnerability of instinct itself? Are there systems in our own biology that are just as open to outside manipulation, and we simply haven't met the thing that's evolved to exploit them yet? Drop your answer in the comments. I genuinely want to know where your mind goes with that. And if this video made you question what it even means to be in control of your own behavior, hit that like button and subscribe. We go this deep every single week.